Greetings, this is Lagrange theorem. This is basically saying ratio between the order of a group G and its subgroup H is some natural number. So these two are integers because order of a group in mod of its elements is an integer. If you divide a group's order by its subgroup, it should give a positive integer. And Lagrange theorem furthermore specifies that that's equal to the index of subgroup H in G. And I'm not going to go deeper into this because I'll suppose that you know this, because here we want to focus on the proof of this. All right, we want to focus on the proof of the Lagrange theorem. So here I just repeated it. Basically, the amount of distinct cosets of a subgroup in a group whose subgroup it is going to be equal to the ratio between the orders of those two groups of the group divided by its subgroup's order. And this is the definition of a coset. So if you have this is a left coset, but if we're dealing with abelian cases, then it doesn't matter if it's a left or right coset. But let's say we're talking about left cosets here, where the G is on the left. But basically, this is an element from the group G with every element of the subgroup H put into operation with it, and that will generate a set. So the set generated when you take one element from G and put it into operation with all the elements of its subgroup H. And that's basically as H spans the capital H subgroup H, as an element from H spans all of H. Let's take all the products G times H, or operation between G and H. That shows an element from G and every individual element from the subgroup H. Alright, so this is Lagrange theorem, and this is definition of a coset. And now let's talk about the proof. So how to do the proof? Well, what we want to prove is that it is a whole number when we divide the order of a group by the order of its subgroup, and that it equals to the that will specify the amount of distinct cosets. So let's see. What we will need for this proof is to prove that the map from a subgroup to a coset with one element from the group G, whose subgroup it is bijective. We want to prove it. And what this is a map, because it maps a subgroup H, the subgroup H we're considering, to the coset GH as specified here above. I want to see if it's bijective. So what basically this is doing is it takes a lowercase h, and that will equal to GH, and that will generate all of G times capital H. And how do we find if it's bijective? Well, first of all, we need to prove it's injective, and then that it's surjective. When we prove both that it's injective and surjective, we prove it's bijective. And when we prove that H, a map from H to its coset GH is bijective, that means that the order of the group H equals to the order of the coset. And this is an arbitrary coset, not a specific one. This is any element G from G and a subgroup H. So this says that a coset generated by subgroup H with an element from G is always equaling the number of elements. Its order, the order of this set, equals to the number of the actually this is the same number as the number of elements in that subgroup H. And how to prove it? Well, this map has to be bijective. So to prove it's bijective, we have to prove it's injective and also surjective. So for it being injective, it's injective by, if we take, injective basically means that if we have GH1 equaling GH2, that can only happen if H1 equals H2, where H1 and H2 are in that subgroup H. And why is it so? I can apply negative inverse G to both sides. Alright, and then I have h1 equals h2 by that. So I got there algebraically, or operation, by using this operation of applying inverse g to both sides to the left. So I proved that basically that member of that coset is going to be equal to another member only if those h values, those members of the subgroup h that make it are equal. Okay, if they're different, if the g is same and the h is different, then it cannot be equal. It can only be equal if h1, h2 are actually equal. So that's making it injective. Okay, we can have the same output y only if the inputs x are same. If it's the same input, not the same output for more same input. So we see injectivity here. And now let's also look at surjectivity when we have a little more space here left. Surjectivity will work the way that we know that any member of the coset GH has this, that is basically equal to g times h for h inside that subgroup. So what surjectivity asks us, that every output has some input that we can trace it back to. And that's true. We can take any member of the coset and find a lowercase h inside that subgroup h that caused it to exist. So yes, it's surjective as well. So now we proved it's both injective and surjective, and therefore it's bijective. So we proved that this this map from h to its coset gh is bijective. Therefore we proved therefore we prove this. Okay. We prove this. The order of the subgroup H is equal to the order of its coset, of its arbitrary coset. And thanks to this, and thanks to knowing that cosets separate group into equivalence classes, because there's a finite number of cosets, we know that if we have some coset, if we have a group G, and then we separate into cosets, so that will be G1H, we have, let's say, 4 cosets, G2H, G3H, G4H. Then for every G in G, this is equal. We already have this from here. And for that reason, the group is separated into subsets that are equal in order and that are equal to the order of the subgroup. So the subgroup's order has to divide the order of the group G whose subgroup it is, and that's the idea here.